All right, so in this podcast, we're going to talk about trends on the periodic table. All right, so to understand trends on the periodic table, you first need to understand this thing called effective nuclear charge. Effective nuclear charge is basically the charge of the nucleus minus any of the shielding effect that it's occurring because of the core electrons. So the nucleus is positive because of the protons, electrons are negative, so there's an attraction there, okay? Now, the very outer shell of electrons, the valence electrons, they experience less of a pull from the nucleus because of all these other electrons that are closer to the nucleus, the core electrons that are kind of blocking some of that positive attraction. So we call that the shielding effect. But in essence, what you need to know is that the charge of the nucleus, or the effective nuclear charge, has a lot to do with trends. All right. So the size of atoms, or the radius, basically, which is the distance from the nucleus to the outside shell of electrons, is what we call atomic radius, okay? So that is all related to the size. So atomic radius decreases going from left to right on the periodic table and increases going down, so from top to the bottom. All right, so let's talk about the top to the bottom first, periodic table. What you have going on is every time you move to the right on that same row, you get another proton in the nucleus, right? So that extra proton in the nucleus is pulling that shell of electrons closer. So every time you get another proton, it pulls that shell in tighter. So that's why the atom itself gets smaller as you go across a row, because that proton, that extra proton, just pulls that shell in tighter and tighter. The top to the bottom is very easy to understand because the more you go down the periodic table, the more shells or rings of electrons you get. So obviously it's going to get bigger, right? Now going from left to right across. All right, ionization energy is another periodic trend we're going to talk about. Basically what it is it's the amount of energy required to move the outermost electron from the atom. Now, you can have first ionization energy, second ionization energy, third ionization energy, and so on. Basically what that means is the first ionization energy is the energy required to remove the first electron. Second ionization energy is the energy required to move the second electron. And then it continues on and so forth. Now, trends in this. So, as you move from left to right across the periodic table, the ionization energy increases. So it's harder to remove the electron. That all goes back to that proton. So as you move from left to right, you get more protons in the nucleus, and because you get more protons, that means it's harder to remove an electron from that ring because that nucleus is pulling harder on that electron. There's more of an attraction between them. So as you go from left to right, you have an increase in ionization energy because you are getting more protons. You have a higher nuclear charge or effective nuclear charge. All right, as you go from top to bottom on the periodic table, you have a decrease in ionization energy. Now, that's going to make sense, hopefully, because as you move down the periodic table, you get more rings, right? More rings means that those electrons are further away from the nucleus. And you know from the Coulomb's law podcast that the further away those valence electrons are from the nucleus, the less force of attraction they are experiencing. So if they're experiencing less force of attraction, you can remove them easier. All right, so we already talked about the fact that as you go across a row or across the periodic table from left to right, it gets harder to remove an electron because you get more protons, right? Higher effective nuclear charge. However, there are some exceptions to this. there are two that we're going to talk about. The first one occurs between the second group on the periodic table and the third. So between the alkaline earth metals and then that column with boron. Okay, so you would expect that boron or, boron would have a higher first ionization energy than beryllium, but that is actually not true because it is in the p orbital. This is outer electron, its valence electron is in the p orbital rather than in the s orbital. Because it's in the p orbital, it means it's actually a little bit further away from the nucleus. And so because it is further away from the nucleus, it's actually easier to remove it than it is to remove that valence electron in beryllium, because beryllium's is in the s orbital and it is closer. Okay? All right, the second exception to the first ionization energy trend occurs between groups 5 and 6. So on the periodic table, it occurs between the nitrogen and oxygen group. So you would expect that oxygen, based on the general trend, would have a higher first ionization energy because it has more protons. But actually, what is happening is it's going to have a lower first ionization energy because it is the second, it's the first electron in the p orbital that becomes paired. All right, so if you remember orbital diagrams, right? So orbital diagrams are the little boxes. All right, and this is a p orbital. So group 5 is going to have 3 p electrons. So they spin up, right? So everybody goes in an orbital, okay? Now, the sixth row has sixth column, the oxygen column, has 1 extra because they're P4s. So it has this 1 extra. This right here, this electron-electron repulsion actually makes it easier to remove this like odd man out electron than it is to remove it from a straight just 3p orbital or a p3 orbital, because they're all paired up, and that's actually quite stable. So this electron-electron repulsion that you get in that sixth column is what causes that discontinuing, I can't say the word. It causes the exception in the trend. All right, now looking at ionization energies can tell us actually a lot about how many valence electrons a element has. So, for example, sodium, if you look here, this right here, let me change this, okay. This right here, this is first ionization energy, second, third, fourth, so on. So first electron removed, second electron removed, third electron removed, okay? Now, if you remember, sodium has 1 valence electron, right? So after you remove that 1 valence electron, now you're going down to another shell. So you're going 1 more shell in, 1 more ring in. That's why you see this huge jump in numbers. It's going from 495 to 4562. So there's almost a 10-fold difference between that first and second ionization energy. We call that the quantum leap, which means it jumped down a ring. So if you have an element and you can see where the quantum leap occurs, that tells you, so there's our next quantum leap for magnesium, it can tell you how many valence electrons it has. So you look for the quantum leap, so like here, big difference in values, okay? And then you count the electrons or the ionization energies that occurred before the quantum leap, so 3 valence electrons, okay? And then here again, so there's our quantum leap, all right? And then that means that this has 4 valence electrons, all right? And so on and so forth. So that's how you can analyze ionization energy data to tell you some information about the identity or the number of valence electrons in that atom. All right, the next trend we're going to talk about is electronegativity. Electronegativity is basically it's a measure of the atom's attraction for a shared pair of electrons in the bond. So it's basically when you're in the bond, in a bonded pair, in a shared pair, which the atom that's going to pull that pair closer to itself, okay? All right, so going across, electronegativity increases. It increases for the same reason as ionization energy and atomic radius going across. So it increases because you're getting more of the getting more protons in the nucleus, which means there's a higher attraction. Okay, so like for example, F, fluorine, is going to pull any shared pair that it has in a bond closer to itself because it has more protons. Now please note that the noble gases over here have no electronegativity because they are not known to bond, okay? There are a few exceptions to that, but they have no electronegativity officially. So fluorine is the most electronegative element on the periodic table. All right, now going down the periodic table, you have decreasing electronegativity. All right, this is for the same reason as atomic radius and ionization energy. As you move down, you get more shells of electrons. The more electrons you get, the less attraction there is between that nucleus and that outer shell because they're so far apart. So the the least electronegative element on the table would be here because it is at the very bottom. So it has a whole bunch of rings of electrons, and therefore it does not pull any shared pairs very close to itself as compared to like fluorine or even somebody over here. Okay? All right, the next periodic trend that we're going to cover, and the last one, yay, is the size of the ion. Ion means it has a charge, doesn't have the same number of protons and electrons. And this is all, it's also called ionic radius. Okay, so first thing I want you to notice is that there is not necessarily a definite trend here. Okay, there's two different things going on. So there are cations, which means they have lost electrons, and then over here are anions, okay? So you have to look at these two trends separately, okay? So cations, which are positive ones, they've lost electrons, okay? They get smaller as they go across because they're getting more protons, okay? So they're getting more protons, it's pulling that outer shell in closer, all right? And then anions, which means they have gained electrons, okay, they have a negative charge, they've gained electrons, okay, again, same trends, they get smaller as they go across, and they get smaller as they go across because, again, they're getting more protons. So what I really need you to understand here is that there is a difference between cations and anions. So in general, cations are smaller, okay, and anions are bigger, okay? So, and then the trend within the two is that they both get smaller going across. It just, it starts over when you go from cation to anion. All right, now going down, they have the same trend, okay? So they increase in size as they go down because, as you guessed it, they have more shells, right? So they get bigger. All right, now, we're going to talk about this other thing called an isoelectronic series. So what isoelectronic means? Isoelectronic means that you have the same number of electrons, even though maybe you're not the same atom. So like for here, we've got lithium 1+, which means it has 2 electrons. And then you've got oxygen 2-, which means it has 8 electrons. And then the 2- means +2, so that's 10 electrons. And then magnesium 2+, which means it lost 2 electrons. So it went from 12 to 10. Okay, so these two are isoelectronic with one another, meaning they have the same electron configuration because they both have 10 electrons. So how do you know who's going to be bigger? Okay, so who's going to be bigger in an isoelectronic series is all dependent on how many protons they have in their nucleus. So oxygen only has 8 protons, magnesium has 12. So that means that magnesium will actually be smaller because it has more protons in the nucleus, and it'll pull those 10 electrons closer to itself.